Welcome to this session on overcoming the instability of the grid. My name is Keith McLean-Martin. I'm the technical manager at Pillar UK with nearly 20 years experience in engineering critical power solutions. So in order to understand the increasing problems of instability in the grid today, we need to understand how the grid has evolved, and this will start from the initial formation to what we actually see today. After we have this understanding, we can then realize the increased risk of supply issues, and we will look at the UPS solutions available that will protect you from them. Finally, we will show that there are many ways that UPS can be integrated into your facility to offer you the most appropriate protection required and the best suiting for your infrastructure. So the 1930s, this saw the formation, construction, and first connection of the national grid. Initially, it was formed with 7 main control centres. This in fact happened due to the threat of World War II and the government's need to protect national infrastructure. In the 50s, the demand for power was going to exceed the ability for the network to actually supply everyone in the future. So a 12-year programme was put together to implement the 275 kV supergrid. This decade also saw the formation of the Central Electricity Generating Board that was focused with keeping the lights on. Now, the 60s, again, as demand continued to grow, the highest power users concentrated around the major cities. A project construction group was formed to deliver the next supergrid. This time, we're up at 400 kV. 4 years after this group's formation, construction actually started on this very supergrid. Now, the 70s, this saw the formation of the regional engineering departments and Northern London getting connected to the more efficient 400 kV grid. We also saw the construction of start for the pump storage facility in Snowdonia, Norwich. That's the first bit of real stored power on the network that was you'll become more familiar with as we go on. Now, initially, most of the power was supplied by coal-fired power stations. This map shows the major facilities with all bar 3 actually shut down now. The UK, though, is in fact full of a great many power stations ranging from 1 megawatt up to nearly 4,000 megawatts in capacity. Now, this map here includes actually all the facilities, even those that have since been closed or even demolished in some circumstances. But the majority of generation that once was coal has now actually become combined cycle gas turbine generation, or CCGT. During the grid's evolution, nuclear generation has also been added, and this came in from about 56, which is included as a clean form of power generation, as carbon isn't released into the atmosphere as part of the process. There are, however, obviously a few other byproducts that are less pleasant, but can be dealt with safely. Currently, we've only got 8 reactors in operation, but 3 more are planned over the coming years. And looking at this distribution of the power generation that we see across the country, it's clear to see that there are certain concentrations. And this itself has led to the layout of the supergrid for the national grid network at 275 and 400 kV as we see here. This network was built focused on these concentrations of power generation, which were mostly all high-power synchronous machines offering high inertia levels with high fault current contribution, and resulting in a really stable network and predictable performance during fault scenarios. However, now these legacy power stations no longer really offer the best forms of generation to support our needs of the future and the grid of the future. So, over the last 20 years, renewable forms of generation have been added to this network. The grids and government are targeting to actually achieve 100% renewable generation by 2035. That's just over 10 years away. We've seen considerable growth in renewables such as wind, solar, hydro, but these forms of generation are intermittent and use inverters to generate a synthesized waveform, not a synchronous machine. What is interesting to see is perhaps the intermittency of this generation. A really good example of this is the install capacity of solar is up to 13 gigawatts in 2018. That's approximately 25% of the overall install capacity. But if you look at the graphs on the right, the share of actual generated terawatt hours, it only delivers about 10% of renewables for that year. This helps to demonstrate the intermittency of some of these forms of generation against their capacity. The locations for these renewables isn't actually restricted in the same way that coal, gas, and nuclear generation has been. In fact, it's actually often best in a completely different location. So if we think back to the national grid infrastructure, these sources are now being connected at a lower voltage level within the actual distribution network operator networks. That's up to about 33 kV. Therefore, the distribution of this renewable generation doesn't actually match the existing planned infrastructure. So this adds a lot of complexity and stress to these lower voltage networks, as these are no longer distributing from the central supergrid to the users. Now what the DNO is actually offering connection of this distributed generation, seeing power flow in all sorts of directions throughout its own local network operations. What you see, though, the final map here showing storage introduces one such source being used by the national grid to manage network. First of which obviously was talked about in Norwich in the pumped storage system. This is becoming more and more important, but there are many of these sources used by the national grid now to deliver sort of demand-side response services. So variable renewable energy sources, or VRE, make for a really complex challenge to balance the supply and demand. The national grid has introduced these additional services that can be called upon rapidly to really help support the grid during different events. These can actually be delivered in a number of different ways, whether by diesel or gas generators, or, as we said, battery energy storage systems, or pump storage. But even, it's possible that sites themselves can actually disconnect from the grid and operate in Ireland, and these services can then be supported by those clients. In fact, we are already helping a number of our clients to deliver some of these services across several of their UK sites. They each then have their own requirement for these services, but they do offer opportunities to actually generate revenue from your integrated site assets, as these are all paid for services. And sometimes you're even paid for the service just to be stating that you're available for use without delivering any power. However, despite all of these balancing services, I think most of us will probably remember the 9th of August in 2019, when there was a major event on the national grid network causing critical infrastructure outages. So on this fateful day, everything was in fact running according to plan, and the general predictions were being met. There was then a lightning strike north of London. Now, this in itself isn't unusual, and they handle actually more than 1,000 strikes a year without any interruption. In this time, the fault cleared and the system reset, but there was a loss of 500 megawatts of generation. Unfortunately, within seconds of this, two large generation plants, one a gas and one an offshore wind farm, disconnected with a loss of nearly 1,400 megawatts of generation in total. Now, this saw a significant frequency drop. The ESO plans for these events and actually keeps backup generation to match the single largest generation station on the grid, which at the time was 1,000 megawatts. They also had 475 megawatts of battery storage that they could call on. However, given all of that spare capacity in reserve, there was still a deficit. So we had 1,475 megawatts compared to 1,900 megawatts. Obviously, the deficit here, the frequency dropped yet further. We reached 48.8 hertz, and this resulted in secondary protection operating, causing the loss of power to approximately 1 million homes in the country. Now, after this frequency began to recover, we saw critical infrastructure with loss of power, which was a major incident in the world of the government. Following this event, they rapidly rolled out the loss of mains change program. This was an attempt to avoid similar events in the future. This actually changes the detection method for loss of mains, therefore no longer allowing vector shift, and they're also requiring the increase in the rate at which the frequency can change, but not the actual ultimate frequency limits that are applied. But what does this actually mean? Well, the grid is no longer as stable as it once was. It's not locked to that fixed 50 Hz frequency as it used to be. So the stability cannot be maintained, but they're trying to avoid the early disconnection of distributed generation sources, which cause an event to rapidly worsen when perhaps the system might in fact be recoverable in other circumstances. This is an unavoidable result, though, of the use of embedded VRE that use inverters to generate a sinusoidal waveform rather than the synchronous machines used originally. So to further combat these issues, Grid is actually adding further services to help with other aspects of the grid now affected by the change in generation sources. Probably the two most significant issues are, in fact, loss of the fault current and a reduced system inertia. Although I think voltage issues are rapidly becoming a more significant problem, in fact. They're actively monitoring the network inertia on a real-time basis to manage their generation sources. So they're using that to make decisions as to which generation is used. So this could see actually the use of legacy generation, such as coal-fired stations even, being used in preference to renewable sources in order to actually protect the network. Now, these issues aren't a singular issue affecting the whole of the network in one single way. They vary significantly across the different regions of the country. But as a result of these changes to the grid, we are actually seeing increased power supply issues at the site level now. Now, the main power issues are well known to most in the critical power world, and these include things voltage fluctuations, frequency deviations, and perhaps other transitory problems. As these issues are experienced more frequently, disruptions to production and process can become more problematic. This issue can also worsen as new production equipment will often integrate new electronics, sensors, and control systems, all of which are more likely to be susceptible to these power supply issues. But it's not just IT equipment, in fact, that can be affected by power supply issues. You've got drives, you've got motors, you've got fans and mechanical systems. With a loss of supply, that can quickly affect the production, causing either a loss of product or in fact even damage to buildings in the worst case scenario, as we've heard happen. So this will quickly have financial impact, not only as a direct result, but perhaps actually as a consequence, whether that's with brand or reputational issues being affected by these scenarios, these events now. Needless to say, there are, I'm very pleased to say, cost-effective solutions to these very issues, as otherwise I wouldn't be here today. So an uninterruptible power supply, or a UPS, it's not there just to protect in the event of a complete loss of power, which is what most people think of them to be. They are actually there offering constant power conditioning to your critical loads. So they provide the loads a constant clean supply of power, irrespective of the quality of the supply from the grid, or in fact from generation sources, or even from no grid at all. They also offer isolation from your loads as a client from the grid. So loads such as variable speed drives, perhaps large motors, fans again, these can actually impose harmonics or can draw power with a really poor power factor from the incoming supply. These, in fact, issues can in fact all add to the grid supply problems that you're actually already starting to experience and worsen the effects of them eventually. But they do actually have a financial impact as well, because a lot of the time network suppliers will actually penalise clients for drawing poor power factor, or in fact for imposing harmonics on their network. And this is probably going to become more prevalent as supply issues are seen more widely on the grid supply. So what products are there? There are many products or technologies out there, but perhaps the best way to differentiate between the overall performance, flexibility, and the maintainability is considering their topology. These topologies differentiate the technologies by how the energy store is coupled to the UPS system. So here we have mechanically coupled, or MC, and electrically coupled, EC, UPS systems. Now, the MC UPS is a single drivetrain consisting of an alternator, an energy store, and a diesel engine. This makes for a very complex system with nested bearings, and actually a really long drivetrain, which can be subjected to really high torsional forces as a result. So it's quite a stressful environment for them. The energy store is actually mounted in line, and they use a speed difference relative to the main shaft speed to allow the transfer of energy to and from for charging and discharging of the energy store. The good thing with the MC systems is they offer a really compact footprint for very high power systems, but they are restricted by their inflexibility. So this topology is only available from a few suppliers, and there tend to be probably fewer applications that really only require this topology as a solution. The EC UPS actually differentiates by using a DC bus to integrate the energy store. Now, this allows anything from batteries to flywheels to supercapacitors and many other sources, even compressed air, to be used. They offer the flexibility to tailor the solution to meet all the requirements. And now there is actually a further differentiation of products within this EC topology. As one uses natural generation with a synchronous machine, while the other uses actually a synthesized waveform from electronics. Now, both of these EC systems, they offer critical load protection, but sometimes they're best suited to slightly different applications. So the conventional static UPS are generally a smaller power device operating at low voltage. They offer a very compact footprint for smaller, perhaps IT system loads, and they can offer support to larger networks of system loads, but they do require multiple machines to be parallel together. Now, the natural generation with the synchronous machine used by the Uniblock range of products does allow the integration of these systems at low voltage or high voltage. That's anywhere up to 33 kV, in fact. And they're very well suited to support very difficult mechanical type loads, whether these are high power devices with inrush, or perhaps drives run off variable speed drives, which impose harmonics to the supply. But they can just actually as easily support IT equipment, or in fact any combination of the different types of loads that you might find in a facility. So the main energy storage systems in the market are either perhaps chemical or kinetic storage systems. Batteries are often considered now to be a really green solution. Whether you talk though about lead acid or lithium ion, that varies. We must remember that the life expectancy and the recyclability of these products differs greatly. Lead acid is widely recycled, achieving upwards of 95% recycled materials. While the recycling of lithium-ion batteries is currently in its infancy, such that recycling is very difficult. And in fact, these batteries can be very, very dangerous if in fact mishandled. So there are a lot more controls and hazardous measures that need to be considered when recycling these as well. Also, while these chemical stores are in operation at your site, they must have environmental conditioning to achieve their optimum performance. Too hot, and the life is in fact cut short. Too cold, and they won't in fact deliver the required performance you need. Conversely, though, the flywheel solutions offer a very compact footprint with longer lifetimes and actually a very simple recycling process at the eventual end of life. Their ability to recharge quickly is much, much better than the chemical systems. So they can do what we call the ability to repeat duty very, very quickly. Now, if we're seeing more frequent short-term outages, that's going to become more and more important as we see lots of these short-term fluctuations to the supply. Here we summarize perhaps some of the differences between the topologies and certain attributes that might affect their ability to integrate into the desired system or configuration that you have. What drives you to one technology or other, whether that's the energy store you're wishing to use, the ride-through times, whether you've perhaps got existing generators, or alternatively, perhaps the infrastructure you've got is already at the high voltage level, or finally, perhaps even just the load capacity that you're looking at. Any one of these might drive you down to one solution or another. So it's just a quick bit of an overview of these different solutions to offer the protection to your facility, to those critical supplies that require it. So now let's talk about perhaps the integration now and operation within your infrastructure rather than just the products. Starting with this, perhaps it's important to consider, are your operations 24/7? Or do you in fact have some periods for planned shutdowns that would allow maintenance operations to take place? If not, then it may be worth considering adding some additional redundancy to secure your infrastructure. So here we see a basic single module system. Redundancy can be added directly to the system, or alternatively, if infrastructure permits, and it's much better, a second system could be integrated in this manner. Now, this reduces the single points of failure in your overall system and really does improve the reliability quite considerably. Now, all sites do have different power requirements, and it's not always possible to use a single module to support the load. Therefore, paralleling these modules together allows the system power to be increased to deliver the requirements for the site. There will come a point, though, that protection may best be integrated at HV rather than LV. So that can be driven by the power demand, but it can, in fact, also be affected by the existing infrastructure. Perhaps the location to site the equipment relative to the point of use, possibly sort of multiple distribution systems spread across a large facility, and therefore you want a centralized UPS system to support these multiple locations, but they could be hundreds of meters away from each other. So all of these can influence your technology choices. So how you integrate into your facility is important to understand as well. Now, while the national grid is experiencing more fluctuations in supplies, they are still typically quite short, a few seconds generally at a time. Therefore, for some operations, it's not actually necessary to integrate a long-term backup such as a diesel generator. And in fact, economically, it's not always worth it because, I mean, diesel's becoming really expensive now, and no longer can you use red diesel in standby power generation applications. But in a lot of sites, it can't always be avoided. But where you do actually integrate your diesel, you have some options, and that can actually influence and affect how you operate your system. So the conventional configuration would see your diesel generators integrated upstream in what is a centralized generation plant. This allows the easy export of power independently of the UPS plant. The direct connectivity isn't there, but it does mean you do need a bit of ride-through time to get from between mains and generator, and for the switching of the supply to connect through to your UPS. Alternatively, we could actually go for what we'd term as an embedded system, or perhaps some people would view as a drop solution. There are alternatives such as a D-RUPS where we electrically connect this, but that is product specific. It does give you the advantage that you can integrate into an HV network with the use of a standard LV generator, which which definitely has its advantages here. So that's an alternative mechanism. Finally, downstream. This is unusual, and not all UPS can do this. With the DNO networks that are really overstretched, and we talked about being stressed earlier, this solution can actually allow overloaded grids to integrate where there are in fact limitations on the connection capacities due to the isolation between the generation and the main connection. This also can actually simplify any of the G99 requirements and application processes. Recently, the ENA considered DRUPS or the downstream generation systems to be uncontrolled storage and in fact not a generator. Therefore, a G99 application isn't really required. But always check with the DNOs. They always interpret these slightly differently, but understand that there are differences then in how DNOs and the ENA will view these solutions. You may, however, have some generation already on site, or you may wish to use a different sort of generator, perhaps a greener solution with a gas CHP. These are all possible, but the integration is slightly different with the UPS. Now the UPS is not just a UPS. It turns out they're also a stabilizer, because often perhaps an old generator or a gas engine are not very good at managing load changes. And typically at manufacturing facilities, there's often production processes which see significant load steps and load changes as a result. What you could use is the use of a flywheel-based UPS system allows these loads to be balanced very, very quickly and efficiently, in fact, without limiting your generation choices. So offers a great opportunity to work with the gas engines, the CHP, and perhaps benefit from some of these demand-side to response services. One such example is actually shown here. Now, we allowed for the integration of a new CHP to run in island mode while still delivering a really highly reliable power supply to a production facility, despite that facility imposing 20% step load changes as their production processes changed. And the CHP would not be able to handle it unless it had the main grid available. So the other issues are the DNO restricted the size of their supply. Therefore, they had no other choice other than to generate their own power. So this was also restricted by the fault levels in the local area. So, and the addition of the UPS generator upstream now of the generation allowed isolation between the grid and the site. Ultimately, that isolation allowed this whole facility upgrade to actually go ahead as planned. Otherwise, it could have been completely thrown out or very, very expensive new connections to the network required. This solution also, in fact, allowed a limited power export to run through the UPS out to the grid, allowing for some revenue generation from these assets. So we've obviously taken quite a quick overview of the whole system, about the national grid, how it's evolved, where it's moved to, and obviously where it's still moving to with the major electrification of all systems wherever possible. We've also kind of taken a look at what these supply power issues mean, and perhaps how you can protect your site from that with the different UPS topologies and technologies and the different energy sources. Finally, looking at the integration to support existing facilities and stabilize different power requirements. Hopefully it's given you a quick little bit of an overview to see and understand how this might all work together to protect you from the more frequent power issues that are going to be experienced as the grid instability worsens. When we ran this session live at M&E Expo in June, we had a number of questions come in. Now, we'd like to take this opportunity to address these questions here again, but I would really like to, if you have any questions, please use the platform here to submit your questions. they'll get passed through to us, and we'll come back to you as quickly as possible with some responses and answers to your questions. And we'd be really happy to hear what your thoughts are on this and any experiences or questions you've got around this. But moving on, the questions that we had, first off, are there any signs that the stability of the grid will improve anytime soon? Well, I'm really sorry to say, in truth, the stability is probably only going to get worse over the coming years. However, that is over the coming years. There is light beyond that. The stability will ultimately start to improve as there are more systems there to help provide that stability. As we get newer forms of renewable generation, additional storage systems in place, as we get more intelligent power systems, as the information of Internet of Things broadens and expands, you'll start to see the interconnectivity of devices, which allows power saving to be dynamically adapted according to the needs of the grid. So this will find this massive interconnectivity now, all the way from the national grid, all the way down to the very small singular devices that could be anything from your fridge at home to your electric vehicle charging point at home. So in short, though, in the short term, the stability of the grid is probably going to get worse. There's talk of rolling blackouts this winter, but in the future, years down the line, we're talking sort of 5 to 10 years down the line, we certainly see there's going to be improvement in that. But there will always be an intermittency that is always a risk. So it will always be balanced on a fine knife edge. Second question we've got here, how much of a problem are frequency shifts to a critical process? And perhaps what sort of magnitudes are we talking about? So perhaps talking about the magnitudes first. So the national grid, while they've introduced this increased rate of change, I said that the ultimate limitations that they're trying to manage the network to haven't changed. That's still a tolerance of 1%. So that means they're trying to deliver power at a frequency anywhere from 49.5 to 50.5 hertz. But what we do know is that a lot of production facilities, a lot of drive systems, control systems, actually use the frequency of their incoming supply as a timing clock. It's there, it's a constant, it's there available for everything to use. So if we start to see significant shifts or rapid shifts in that frequency, the risk is that we're going to start to see more errors occurring in production processes. And obviously with those errors, we might start to see loss of product, loss of monies, loss of time. And obviously this is a financial impact to the business. So ultimately the protection that's required is still there and going to be needed as we start to see those frequency shifts happening more and more commonly. Perhaps just one more question here. Is it fair to say that a UPS can fully condition poor quality power, including outages? Well, I'm pleased to say absolutely yes, it is. It's no problem at all. Any of the different voltage, frequency, transient states that we talked about, the UPS will fully condition that power and provide the ultimate high quality power output to your critical facilities without any further issues. Ultimately, your power protection is the major critical function. Even if you're doing any of these grid services, they will always, every UPS will always bias your critical loads over those demand services being offered to the grid. So I'd like to say thanks again for your time. I do hope you found it interesting, this session about overcoming the instability of the grid. And we look forward to hearing from you with your questions. Thanks again for your time, and hope you enjoyed it. Thanks very much.